When an occupancy is not defined in National Electrical Code Table 220.3, A. The electrical designer can utilize the actual fixture volt amps for load calculations. This approach aligns with the principles outlined in Annex D, specifically Example D3 within the National Electrical Code. Example D3 underscores the requirement to employ the larger value between the actual connected load and the stipulated lighting loads found in Table 220.3. Therefore, in instances where the occupancy in question lacks specific listing within Table 220.3, it is deemed appropriate to utilize the actual fixture volt amps for accurate and compliant electrical load calculations. The National Electrical Code serves as the cornerstone for safe electrical installations. Understanding its provisions is crucial for electrical designers, contractors, and inspectors alike. When calculating electrical loads, the National Electrical Code provides specific guidelines based on occupancy type. Table 220.3 of the National Electrical Code outlines general lighting loads by occupancy. However, situations arise where the occupancy type is not explicitly listed in this table. In such cases, the electrical designer must determine the appropriate method for calculating the lighting load. The National Electrical Code offers flexibility in these scenarios, allowing for the use of actual fixture volt amps. This approach is supported by Annex D, Example D3, which provides further clarification on load calculations for various occupancies. Annex D serves as an informational resource within the National Electrical Code, offering examples and supplementary details to aid in the application of its requirements. Example D3 specifically addresses store buildings, but its principles can be extended to other occupancies not listed in Table 220.3. The key concept is to compare the actual connected load with the lighting load specified in Table 220.3. And use the larger value for the calculation. Since the occupancy is not listed in Table 220.3, the actual fixture volt amps become the primary basis for determining the lighting load. This method ensures that the electrical system is adequately sized to accommodate the connected lighting fixtures. To accurately calculate the actual fixture volt amps, the electrical designer must gather information on each lighting fixture, including its voltage and amperage requirements. This data can be obtained from the fixture manufacturer or product specifications. Once the voltage and amperage are known, the volt amps can be calculated using the formula volt amps equals voltage multiplied by amperage. For example, a lighting fixture with a voltage of 120 volts and an amperage of 1 amp would have a volt amps rating of 120 volt amps. After calculating the volt amps for each fixture, the electrical designer must sum the values to determine the total lighting load for the occupancy. This total load is then used in subsequent calculations to determine the appropriate size of conductors, overcurrent protection devices, and other electrical equipment. It is important to note that the use of actual fixture volt amps is subject to certain limitations. The National Electrical Code requires that the calculated load be sufficient to meet the minimum lighting requirements for the occupancy. These requirements are typically specified in other sections of the National Electrical Code or in applicable building codes. If the actual fixture volt amps result in a load that is lower than the minimum required load, the electrical designer must increase the load accordingly. This ensures that the occupancy is adequately illuminated for its intended use. In addition to meeting minimum lighting requirements, the electrical designer must also consider any applicable energy efficiency standards. Many jurisdictions have adopted energy codes that mandate the use of energy-efficient lighting fixtures and control systems. These standards may limit the maximum allowable lighting power density for certain occupancies. The electrical designer must ensure that the lighting system complies with all applicable energy efficiency standards. The process of calculating lighting loads for undefined occupancies involves several steps. Firstly, identify the occupancy type and determine if it is listed in Table 220.3. Secondly, if the occupancy is not listed, gather information on the voltage and amperage requirements of each lighting fixture. Thirdly, calculate the volt amps for each fixture using the formula volt amps equals voltage multiplied by amperage. Fourthly, sum the volt amps to determine the total lighting load. Fifthly, compare the calculated load with the minimum lighting requirements for the occupancy. Sixthly, increase the load if necessary to meet the minimum requirements. Seventhly, ensure compliance with all applicable energy efficiency standards. By following these steps, the electrical designer can accurately calculate the lighting load for undefined occupancies and ensure a safe and compliant electrical installation. The use of actual fixture volt amps provides a flexible and reliable method for determining the lighting load in these situations. It is essential to consult the latest edition of the National Electrical Code and any applicable local codes or regulations for specific requirements. Furthermore, seeking guidance from a qualified electrical engineer or inspector can provide valuable insights and ensure compliance with all applicable standards. The NEC serves as a comprehensive guide for electrical installations, but its interpretation and application can sometimes be complex. Therefore, professional expertise is often necessary to navigate the intricacies of the code and ensure a safe and efficient electrical system. Another important aspect to consider is the impact of control systems on lighting loads. Control systems, such as occupancy sensors and dimmers, can significantly reduce energy consumption by adjusting lighting levels based on occupancy and ambient light conditions. When calculating lighting loads, it is essential to account for the effects of these control systems. The National Electrical Code allows for demand factors to be applied to lighting loads when control systems are used. These demand factors reduce the calculated load based on the expected reduction in energy consumption. The specific demand factors that can be applied vary depending on the type of control system and the occupancy type. It is important to consult the National Electrical Code for the applicable demand factors in each situation. In addition to demand factors, the National Electrical Code also addresses the use of emergency lighting systems. Emergency lighting systems provide illumination in the event of a power outage or other emergency situation. These systems are typically powered by batteries or generators and are designed to operate independently of the normal power supply. When calculating lighting loads, it is essential to include the load of the emergency lighting system. The National Electrical Code specifies the requirements for emergency lighting systems, including the minimum illumination levels, the duration of operation, and the types of fixtures that can be used. The emergency lighting load must be added to the total lighting load to ensure that the electrical system is adequately sized to accommodate the emergency lighting requirements. Furthermore, it is crucial to consider the voltage drop in the electrical system. Voltage drop occurs when the voltage at the end of a circuit is lower than the voltage at the source. Excessive voltage drop can cause lighting fixtures to dim or malfunction. The National Electrical Code provides guidelines for calculating voltage drop and specifies the maximum allowable voltage drop for lighting circuits. The electrical designer must ensure that the voltage drop in the lighting circuits does not exceed the allowable limits. This can be achieved by using appropriately sized conductors and minimizing the length of the circuits. In summary, calculating lighting loads for undefined occupancies requires a thorough understanding of the National Electrical Code, applicable energy efficiency standards, and the specific characteristics of the lighting system. The use of actual fixture volt amps provides a flexible and reliable method for determining the lighting load in these situations. It is essential to consider the effects of control systems, emergency lighting systems, and voltage drop when calculating the lighting loads. By following these guidelines and seeking professional expertise when needed, the electrical designer can ensure a safe, efficient, and compliant lighting installation. Remember to always refer to the latest edition of the National Electrical Code in any applicable local codes or regulations for the most up-to-date requirements. Also consider factors such as ambient temperature, humidity, and the presence of corrosive substances, as these factors can affect the performance and lifespan of lighting fixtures and electrical equipment. The electrical designer should select lighting fixtures and equipment that are suitable for the specific environmental conditions. Consider the long-term maintenance requirements of the lighting system. Selecting lighting fixtures that are easy to maintain and replace can reduce maintenance costs and downtime. The electrical designer should also provide adequate access to lighting fixtures for maintenance purposes. In conclusion, designing and installing a lighting system for an undefined occupancy requires careful planning, attention to detail, and a thorough understanding of the National Electrical Code and other applicable standards. By following the guidelines outlined in this discussion and seeking professional expertise when needed, the electrical designer can create a safe, efficient, and aesthetically pleasing lighting system that meets the needs of the occupants. Understanding the broader context of electrical design is also crucial. Electrical design encompasses a wide range of considerations, from selecting appropriate wiring methods to ensuring proper grounding and bonding. A well-designed electrical system is not only safe and compliant, but also efficient, reliable, and adaptable to future needs. When designing an electrical system, it is essential to consider the load requirements of all equipment and devices that will be connected to the system. This includes lighting appliances, HVAC systems, and any other electrical loads. The electrical designer must calculate the total load and ensure that the system is adequately sized to handle the load. This involves selecting appropriate conductors, overcurrent protection devices, and transformers. Grounding and bonding are critical aspects of electrical safety. Grounding provides a path for fault current to flow back to the source, allowing the overcurrent protection device to trip and energize the circuit. Bonding connects all metallic parts of the electrical system to create a low impedance path for fault current. Proper grounding and bonding can prevent electrical shock and minimize the risk of fire. The electrical designer must select wiring methods that are appropriate for the specific application and environment. The National Electrical Code specifies the allowable wiring methods for various types of occupancies and locations. The wiring method must be selected based on factors such as the type of building construction, the presence of hazardous materials, and the environmental conditions. Overcurrent protection devices, such as circuit breakers and fuses, are designed to protect electrical circuits from overloads and short circuits. The electrical designer must select overcurrent protection devices that are appropriately sized for the circuit and the connected load. The overcurrent protection device must be able to interrupt the fault current without causing damage to the electrical system. Transformers are used to step up or step down voltage levels. The electrical designer must select transformers that are appropriately sized for the load and the voltage requirements. Transformers must also be protected from overloads and short circuits. Surge protection devices are designed to protect electrical equipment from voltage surges caused by lightning strikes or other events. The electrical designer should consider installing surge protection devices in areas that are prone to voltage surges. In addition to these basic considerations, the electrical designer must also consider a variety of other factors, such as energy efficiency, aesthetics, and cost. The electrical system should be designed to minimize energy consumption and reduce operating costs. The electrical system should also be aesthetically pleasing and blend in with the surrounding environment. The electrical designer must balance these factors to create an electrical system that meets the needs of the client while remaining within budget. The process of electrical design typically involves several stages. Firstly, the electrical designer gathers information about the project, including the type of occupancy, the size of the building, and the load requirements. Secondly, the electrical designer creates a preliminary design that outlines the basic features of the electrical system. Thirdly, the electrical designer refines the design and prepares detailed drawings and specifications. Fourthly, the electrical designer submits the design for approval by the local building department. Fifthly, the electrical system is installed by a licensed electrical contractor. Sixthly, the electrical system is inspected by the local building department to ensure compliance with the National Electrical Code and other applicable standards. Finally, the electrical system is tested and commissioned to ensure that it is operating properly. The electrical designer plays a critical role in ensuring the safety and reliability of electrical systems. By following the guidelines outlined in this discussion and seeking professional expertise when needed, the electrical designer can create electrical systems that are safe, efficient, and adaptable to future needs. The knowledge of the National Electrical Code Table 220.3. I helps design electrical load calculations in residential or commercial environments.